In 1905, Einstein demonstrated in one of his papers the photoelectric effect. The paper in which Einstein proved the photoelectric effect got him a Nobel Prize in Physics in the year of 1921. But what is the photoelectric effect? One of the main things of the photoelectric effect is that light is constituted by tiny particles named photons. When a photon with the right energy hits an electron, it can be dislocated from its position out of the metallic plate. This is what we call now the photoelectric effect. But it's good to have in account that the energy of the dislocated electron depends only on the energy of the photon, which is given by its wavelength. The intensity of the light only helps in the number of the dislocated electrons, not on the energy of those. Knowing all the theory, we decided to prove the photoelectric effect with a very simple experiment consisting of a house-made electroscope, a UV light, and a zinc plate.
Like before, we are using a simple house-made electroscope to practically prove the photoelectric effect. So I'll briefly explain you in what the electroscope consists and in which way we will combine it with the outstanding discovery that made Einstein worthy of receiving the Nobel Prize, the photoelectric effect. Our electroscope consisted of a glass jar, crossed up with a copper wire that we used as a terminal, where it has a pair of tiny foils waiting in the hook-like bottom. We used a PVC rod and charged it with the triboelectric effect by rubbing it. Normally, the number of positive and negative charges are equally distributed alongside the electroscope. When we approach a negatively charged object, in this case a PVC rod charged with a vinyl strap, the electric charges of the electroscope will flow to the bottom of the terminal, making the foils to repel each other. So when the negatively charged object is close enough to the electroscope terminal, we ground it, giving the negative charges another way to flow, unequalizing the charge distribution of the whole electroscope. By doing so, the foils will repel each other, even with no externally charged object nearby. That's where the application of the photoelectric effect comes in. The experimental idea was to discharge the electroscope with an UV light, which is a light with a frequency between 100 and 400 nanometers, by giving a visual demonstration of how the foils return to their original state. We were counting on using a zinc plate to maximize the visual effect of the foil separation angle reduction. Unfortunately, we weren't able to replicate this experiment we thought. The weather condition, in this case humidity in the air due to the constant rains, was an unexpected obstacle we tackled. Moisture makes the air more conductive, so it can absorb and more evenly distribute excess charges. Due to that, we couldn't properly charge the electroscope as planned. We did try several things to overcome this, such as trying it in a refrigerated place and recreating a dry system to work on using silica gel. We arrived to the conclusion that we needed far better experimental equipment.
So why zinc? As you recall, one of our materials was a zinc plate. This is the part that would actually exhibit the photoelectric effect, the part we would hit with ultraviolet light and where we'll see the current start flowing. So why that material exactly? Now you might recall that when we talk about the photoelectric effect, the part that controls when the metal starts emitting is the cutoff wavelength, or the threshold frequency. They're basically the same thing. But when we're talking about each metal, the part that matters is its work function. Different metals have different work functions. Zinc happens to have a relatively small one, about 4.3 electron volts. This means that if you hit it with ultraviolet light at about 180 nanometers of wavelength, we'll start seeing electrons get torn out of the metal. Well, let me give you some other examples of metals that could also exhibit this effect. We could have lead, which its work function is about 4 electron volts. We would have things like potassium or sodium, which have such a small work function that you could actually see the photoelectric effect just with normal light, as long as it was around the blue spectrum. You can also have things that are very common, such as aluminum. Aluminum has a lower work function than zinc, and as we know, aluminum is very common. So why specifically zinc? Well, let's talk about why the other metals aren't good options. First, I don't think I need to tell you that lead can be problematic because of health issues. We would really rather not be handling lead. But there's also another very important reason, which is conductivity. Lead is not very conductive, so even if we started generating electrons, there is really no guarantee that they would actually make it easily to the part that actually held a charge in our experiment. Aluminum is very conductive, but the way that it's sold means that it isn't very easy to use to conduct electricity. As you may know, they sell it mostly in sheets, and they're very easy to wrinkle. While in zinc, they sell them in these electrode plates. These electrode plates are very easy to use for these sorts of experiments. Now, sodium and potassium have an added problem. They are very reactive. When we're talking about the photoelectric effect, it's important to remember that most of the metal doesn't participate in it. It's only the surface level of the metal. Sodium and potassium react so fast with the humidity in the air that it would actually form a layer of oxide that we would be unable to use for this experiment. Knowing what we know now, what would we have done differently? What other types of experiments could we do to prove the photoelectric effect? Well, the first thing that we think we should have done differently is that the electroscope requires voltage differences greater than 100 volts to actually show any effect, while an electronic circuit could work with voltage differences of less than a volt. We didn't think that we would need such degrees of precision, but looking back from this vantage point, we think that maybe building an electronic circuit would have been a better idea. Then, maybe we should have tried to prove the photoelectric effect in the opposite direction, trying to generate light by stopping electrons. The biggest challenge here would be to build a vacuum chamber, but things like LEDs do it all the time, so we think that maybe it would have been better to do it that way too. Finally, we could have tried to build a pseudo-solar panel, which would work the same way that a solar panel does through the photoelectric effect, but by harnessing ultraviolet light. This would also introduce some problems with air, so we would likely have to build a slight vacuum in a tube. But the biggest problem in our project was that it was so dependent on outside factors. So the thing that we needed the most was things that we could control, a controlled environment, which sadly we didn't manage to do in the time we had with the resources we had.
Finally, which is the photoelectric effect, because it's such a great landmark in modern physics history and in human history. All its applications made possible our way of living and our sustainability as a society. In conclusion, as a learning experience, we learned a lot. The best way to learn is through difficulties and overcoming obstacles, challenges, and other casualties that may come up over the road. We had to deal with a lot of challenges, we overcome some, but we weren't able to consummate the results we wanted. But in the end, it's all about learning, and we learned a lot. We learned a lot about experimentation and the difficulties theoretical and experimental physicists come across when trying to work. We face some natural inconveniences like equipment limitation, adequation of spaces to work, and such things like the climate, which we cannot control and we cannot make a big difference of it, but we're only able to work with it and make the best out of it. Even though we didn't accomplish the results we wanted, we still stick to the idea that the photoelectric effect is very important